All right, in our last lesson, we began looking at a set of numbers that for a long time people believed could not exist. These numbers were called imaginary numbers, but really imaginary numbers are just square roots of negatives, right? And it was thought for a long time you can't take the square root of a negative, therefore these numbers don't exist. Why waste our time talking about them? Until they realized these numbers have to exist and have to be used, so they found a way to represent these imaginary numbers, and they used the letter I, but I actually has a specific value. What is the value of I? Square root of negative 1. It's our most basic imaginary number because all square roots of negatives will be the square root of negative 1 times the square root of something else, right? And we said that with our i's, right, we'll have different powers of I present. We said, of course, I to the first is just represented I. I squared, however, is represented I cubed. And then I to the fourth is a positive 1. So this is perhaps the most useful power of I as far as what we're going to get into in a little bit, where when you create an I squared, it becomes negative 1. But I to the fourth equaling 1 helps us to simplify other powers of I as well. For instance, I to the 19th. How would I turn that into one of these lower powers of I? Quentin?
Take out however many powers of I to the fourth you have, and then figure out what you have left.
Right, because every 4 i's, I mean, this is 19 i's, basically, right? So how many sets of 4 are there?
4.
4 sets of 4 for a total of 16. So this first 16 i's become a 1 times 1 times 1 times 1, so it's just 1, right? So if we take out 16 of the i's, our biggest multiple of 4 in the number 19, it leaves us with how many?
3.
I cubed, and so that becomes negative I. If we had, though, like an I to the negative 7th, well, first of all, what does a negative exponent mean, Jamie?
Reciprocal.
Reciprocal. So we're going to rewrite I to the negative 7th initially as
1 over I to the 7th.
1 over I to the 7th. And now in the denominator, again, pull out 4 i's, or as many 4's as possible. In this case, just one set of 4 i's leaves us with
I cubed.
I cubed, which is
Negative I.
so we get 1 over negative I, or we can simplify this to say, remember, slide the we don't want to leave a negative denominator, so
it's negative 1 over I.
good, negative out front, 1 over I. If we had I to the 21st, let's stay with Jamie.
You would take out all the 4's, and there's 5 of them.
Okay.
So it's I to the 20th, which is just the 1. And now it's just I.
There we go. 20 of the i's collectively make up a 4th power, or 5 4th powers. That's a whole bunch of 1s. So it just leaves us with a single I left. What about I to the negative 18th power, Quentin?
Do the reciprocal, so 1 over I to 18. That would be 1 over I squared.
Good. Take out 16 of the i's.
So that's negative 1.
Good, 1 over negative 1, which of course when you divide just gives you a negative 1. Questions on our fundamental powers of I and how we could use those if we had bigger powers of I, which frankly we won't see often, right? But if we had bigger powers of I, they could all come back to these 4 questions. All right, then let's talk about other square roots of negatives. For instance, something like the square root of negative 12. I said if you have the square root of a negative, your first step is always to pull out your I. Basically, remember, we said factor this like square root of negative 1 times the square root of 12, which it is. And the square root of the negative 1 becomes the I. So essentially, it's as though the negative comes out of the radical and becomes an I, hence pull out your I. But we're not finished because we want to simplify the square root of 12.
So 2I times square root of 3.
Yeah, remember, this is going to factor into 4 times 3, pull out a 2, so 2I times the square root of 3. Notice the radical always comes at the end, numerical coefficient always at the beginning. So the I as a letter or literal value happens to come before. What about the square root of negative 4? What would that become, JD?
It would become 2I.
2I, right? I times the square root of 4, or just 2I. What about the square root of negative 75? Ethan, first thing we need to do? Pull out your I, and then we could factor the 75 into
15 and...
Well, it is 15 and 5, but I can't take the square root of either of those. Just like 12 could be 6 times 2, but you can't take the square root of 6 or 2. So remember, instead of 15 and 5, we want one of those values that I can take the square root of. And we can take the square root of 4, 9, 16, 25, 36, 49, 64, so forth. Help class?
25.
There we go, 25 times 3. So I can take the square root of the 25 back to Ethan to get 5. Also keep the I we pulled out and leave the square root of the 3. If we have the square root of negative 27m cubed or something like this, well, again, take the square root of a negative. First thing we got to do, class? Pull out the I to get I square root of 27m cubed. Of course, the 27 would factor anyone into? 3 and 9, where we're going to take the square root of the 9 to get 3i. We're going to leave the 3, but also remember, we can take the square root of letters. I haven't looked at this very often, but remember to take the root of a power, you're going to divide the exponent by the index. What's our index here? A 2. How many times does 2 go into 3? Once with 1 left. So we're going to leave this 3, we're going to leave 1 m in, but we're going to pull an m out. Now where does the m go?
Before the I.
Does it? Which one comes alphabetically? I comes before M, so we're going to put it, remember, the letters are alphabetical depending on where they fall. So A through H would come before the I, M, I guess, whatever comes after I, J? J through Z would come after it. So again, we just keep the alphabetical order there. I looks like any other letter, it just happens to have a specifically defined value. Questions on all of this? All right, once we were done with imaginary numbers in our last lesson, we then began to look at numbers that are part imaginary, but the other part of them is real. What do we call these numbers? Anyone?
Complex numbers.
Complex numbers. And what's the standard form of a complex number, Quentin? What's a complex number going to look like? Jamie? Remember, it's going to be the form a plus bi. We call this the standard form. Make sure that's in your notes. The standard form of the complex number. And again, a just represents the real portion, and the bi represents the imaginary, because to be imaginary, you got to have an I. B then would be whatever coefficient the I has. Remember that now? And we talked about working with these complex numbers in standard form. We said we can add complex numbers. What do?
Add the reals and then add the imaginary.
Yep, just add the reals together, add the imaginaries together. Subtraction, though, we said, well, we never subtract. We add the inverse. So we would subtract, well, add the inverse of the reals, add the inverse of the imaginaries. What about multiplying a couple numbers that are both in standard form?
Foil.
We'd FOIL, because they're binomials, right? We'd FOIL, but when we FOIL, we'd end up with, as we multiply the last, which would be a couple of bi's essentially, we'd end up getting an I squared. Remember, I squared is? -1. And then dividing complex numbers was perhaps the most annoying process, because to divide complex numbers, of course, we show division using a fraction bar, but to divide complex numbers, we've got to multiply by the conjugate of the denominator or the divisor, and so that involves a sum and difference in the bottom, it involves foiling in the top. Let's take a look at how you did on 13 to 29, the odd. We also had some equations that would involve imaginary or complex numbers in that set of exercises. 13 to 29, the odd, they're on page 180. So go and open your textbooks there if you have not already done so. Page 180, and let's look at those odd numbered problems. Bueno. All right. Number 13. It gave you this equation, x squared positive 9 is equal to 0. What kind of equation is this that has an x squared as its highest power class? Quadratic, but there's no x to the first. So this is an incomplete or a pure quadratic. I use the term incomplete. And for an incomplete quadratic, the key is to isolate the x squared. We're going to ditch that positive 9, move it over, as Jamie started to say, to get class -9. And once we've isolated the x squared, we just take the of both sides. Of course, the square root of x squared. But can you take the square root of -9? Not exactly. We've got to do what first? Pull out your I. Of course, we know the square root of 9 is 3. But since it was our idea to take the square root, we need 2 roots. We're going to say both positive and -3i. Did you get those answers for number 13? Forgot the positive and negative. All right. Number 15, we had an x to the 4th minus 16 is equal to 0. And once again, now this technically isn't a quadratic, it's a quartic, but we're going to solve it much the same way. Let's start by moving the
Negative 13.
as a,
Positive.
and then taking not the fourth root, because we don't know how to take fourth roots, but let's just start by taking a square root of both sides. Remember we said the proper way to take a fourth root would be successive square roots. So the square root of x to the fourth
X squared.
and the square roots of 16, positive 4 and negative 4. And then we're going to take the square root again of both sides. We're going to take the square root of x squared. And we're going to take the square root of 4, positive negative 2. And we're going to take the square roots of negative 4, positive negative 2i, right? And so there's our 4 answers. 2 real, 2 imaginary, 4 roots to the quartic. Successive square roots. Did we get those? Question?
No.
Make sense now?
Mm,
All right. Did you do it in study hall last time?
maybe.
Yeah, no wonder you forgot. All right, number 17. We get an x squared, negative 4x, positive 5 is equal to 0. And now this is not an incomplete quadratic. This is a complete quadratic, right? So we don't isolate the x squared or anything like that. Normally, we backwards FOIL here. We'd say x squared splits into x and x. We'd look at this positive and say, well, that means the signs have to be
Same.
the same. In this case, both negatives. And the only way to split up a 5, 1 and 5, and we check our outer inner. No. Now, if this had been a negative 5, you could do like a negative 5 positive 1 to get your negative 4, but the signs have to match and they both have to be negative. This thing doesn't factor. And so remember we said if you can't actually factor a complete quadratic equation, we're going to use a method called completing the square. Now, if you have to use completing the square, generally that means it ain't going to be rational, real numbers, but very often complex answers. So the first step, remembering completing the square, hopefully what you did in your homework over the weekend, in study hall last hour, is to ditch the constant term to the other side. So we're going to start class by ditching our positive 5 as a negative 5. Basically, you just need to leave some space here too, as the process is called complete the square. And we have to figure out what goes in this empty space that we left. Well, to figure it out, class, we do 2 things to the b value. Half and square. Say it with me, class. Half and square. So if we take half of 4 and square it, I'm going to fill in the gap with a 4. That forces this to be a perfect square trinomial. But if we're going to add a 4 to this side, what we do to one side, so we're going to have to add a 4 over here as well. Of course, the PST we said can factor into a binomial squared, as it says there, to get.
X minus 2.
And then on the other side, we get a negative 5 plus 4, negative 1. At this point, once we've got the binomial squared here, we can get rid of the squared by taking the square root of both sides, right? And the square root, the square just cancel to give me.
X minus 2.
But on the other side, what are the square roots of negative 1? Positive and negative I, right? And then to finish it, just get the x by itself, add the 2 to both sides. When I do, I'm going to put the positive 2 here in the real spot, in the spot of the a, and then the b happens to be a 1, so 2 plus 1i and 2 minus 1i are my 2 answers. Did we get those answers for number, whatever it was? Number 17, I think? All right. Questions?
Positive, negative.
Just forgot the positive. So you had 2 plus I. All right. Questions on this? All right. Helps to have the poster up. All right. Let's take a look at the complex numbers now. Number 19, you are adding, and really straightforward. You add the reals, then you add the imaginaries. So when you add the reals, what do you get on number 19, Jamie?
3x minus 2y.
Well, that was 3x. And then when you add the imaginaries, you got
Negative 2y.
negative 2i. So your answer was
3x minus 2y.
3x negative 2i. There we go. The 3x is the real. The negative 2 is the coefficient of the imaginary, so negative 2i. Number 21. You're again adding. When you add the reals, you get, Quentin? 5. When you add the imaginaries?
12r.
So your answer is?
5 plus 12r.
Pretty easy. Number 23, it says subtract. So in your textbook, I trust you crossed out that and put an addition, but I also trust you changed the next complex number to be a negative 6, positive 5i. So when you add the inverse, Jamie, you got what for your answer?
Oh, for my answer? I have 10i minus 2, but I should switch it.
Right, put the real before the imaginary, so
Negative 2 plus 10i.
good. And again, normally we don't want to lead with negatives, but in the case of a complex number, the real is always listed first, even if it's negative. So negative 2, positive 10i. Number 25 is obnoxious, right? Because we got to multiply here. That means we have to FOIL. And when we FOIL, what do we wind up with, Quentin?
2x squared plus ix minus 15i squared.
Good. Initially, 2x squared, positive 1ix, negative 15i squared. But anytime we see I squared, class, it becomes negative 1. So negative 15i squared becomes negative 15 times negative 1, or
15.
positive 15. And if it weren't for a 2x squared at the beginning, I could combine, right, the first and the last. But you can't really combine. So we'll just put the real first. The 2x squared and the positive 15. List that first. There's your real. And then we'll list the imaginary, the positive 1ix at the end. There's my A. There's my B, I. All right? Questions on that? All right? The one time we'll go out of descending order, though I don't know that I dock you points for being out of descending order necessarily, but technically real before imaginary. Questions on 25? Number 27, same type of thing. We just got big numbers, real big numbers. You got calculator though, so it's not a problem. What did you get when you FOILed here for your initial answer, if you can see it written still? And you might have taken it off. Jamie?
My initial answer is negative 176 plus 381i minus 133i squared.
Good. Initially, in case you couldn't hear on camera, negative 176, positive 381i, negative 133i squared. But that negative 133i squared became a
negative 1. So
well, the I squared became negative 1 to give you
positive 133.
Positive 133 at the end, which you then could combine with the negative 176 to get a final answer.
Negative 43 plus 381i.
Good. Negative 43, positive 381i. Isn't that just hideous? All right, did anyone else get that answer? All right, good. And the number 29, it wants us to divide the 4 plus 5i by the 6 negative 5. And again, remember, we're going to show our division using the fraction bar. But because I is the square root of negative 1, it's a radical value. And you can't have radicals in the denominator. So we've got to multiply top and bottom by the conjugate. What is the conjugate of 6 negative 5i? 6 positive 5i would be the conjugate, right? It's the same thing but with a different sign, so as to make a sum and difference. What you do at the bottom? Anytime you multiply a sum and difference, or you multiply conjugates, 3 steps, class? Thank you, Quentin. Class, square the first, square the last, put a minus sign. Square the first, of course, gives us, back to Quentin. Square the last gives us
25.
and of course we put a minus sign between them. But because the I squared becomes a
Negative 1.
we're always going to have a negative 1 always times another negative, which is always going to give us, class, now a positive in the denominator. So my denominator ends up becoming 61 for the denominator. In the numerator, we still got to do what, Jamie?
A FOIL.
FOIL. And when we FOIL, what do we end up with here?
24 plus 50i plus 25i squared.
And here the I squared, of course, becomes a,
Negative 1.
so this becomes a,
Negative 25.
and so we combine the 24 and negative 25 to get
Negative 1.
plus the 50i. You can leave it this way. You could split it and say negative 161st, positive 50 61st I. This is more of the A plus BI format, but I'll take this answer or this answer, either one. Did either of you have that answer? All right, excellent questions on that. All right, we'll practice with more of that here in just a little bit, but I want to move on to one last concept here in this chapter, or this little section of chapter 9 rather. That's complex equations. Next section of notes, complex equations. Complex equations are equations that are part real, part imaginary. You probably could have guessed that. Equations that are part real, part imaginary. Meaning as you look through them, you'll see some I's sprinkled throughout, but you'll also see things that don't have I in them. So things that have imaginary and things that are not. Generally, complex equations will be two variable. Where I doesn't function as a variable, I functions as a constant square root of negative 1. Something like this, 3 plus I plus x equals y plus iy minus 2ix. Notice we see two variables, x and y. We see some things with i's, some things without i's. You know what you call something without eyes?
Blind.
Blind. Good job. See, smart. All right. Or there was this photographer where I went to school, and his favorite joke, like, you try to get people to smile, people never smile. So you try telling jokes. He wasn't much good at that either. He's like, what do you call a fish without an eye? Psh. See, that's the same reaction, right? People just shook their heads and they still didn't smile for the picture. All right, anyway, what we're going to do, here's your strategy tip. Your key is separate the equation into two separate equations, a real equation and an imaginary equation. So we're going to copy down everything that's real. This 3 is real. That's not. The positive x is real. Equal signs can be both. Okay, so we're going to keep the equal sign. The y is real. That's not, that's not. Make sense? Then in the second equation, we're going to take everything that's imaginary. We're going to take the I, the equals again, the iy, and the negative 2ix. So we're going to separate into two equations, all the real and all the imaginary. With this idea that if there's an I in everything, you can divide I out of everything, and this then becomes 1 equals y minus 2x. And now the I is gone. So the whole reason for separation was if we can isolate all the imaginary together, we can knock the I's out of everything. Now there's no I's left, and that's happy. And notice what we have. A little system of equations. Let's review solving systems of equations. It's been a little while since Algebra 2 when we worked with these, and I don't think we saw any of this in geometry last year. Remember, to solve a system of equations, we could either line up the x, the y, the equals, and the number with each other, and we could actually add those equations together in such a way that x's or y's would knock themselves out. The other option was to, like we see here, get a letter by itself. It just so happened to fall that way, and we could replace that letter with what it was equal to. So my bottom equation could become 1 equals not y, but what is equal to y, 3 plus x, negative 2x. You remember the substitution approach. All right, so if we were to solve using the substitution approach, I'd start by combining my like terms. Negative x, we have 1 equals 3 minus x, and then maybe pull a double switch here. Send the x over as a, and send the 1 over as a negative 3 minus 1, which is 2. Once we know that x is 2, we can plug that in to solve for the y. What's our y value? 5. So my answer to the equation is 2, 5. 2 for the x, 5 for the y. Let's do another one of these. Write this down if you would. 4x, negative 25 minus 5ix equals 24i minus 2iy minus y. Again, we see an equation that has some real to it, some imaginary to it. We want to take this one equation class and split it into two equations. The first equation will be, and the second equation. What's my first equation going to look like here, Jamie?
4x minus 25 equals, well, negative 1.
All right, and then my second equation will say what, Quentin?
Negative 5 equals 24i minus 2iy.
The idea of separating them out is that with the imaginary equation, I can do what, Ethan? The idea of separating the real from the imaginary is that it allows me to do what in the imaginary equation? Well, we do get a system, but what can I do to this lower equation, the imaginary
Right.
equation?
You could drop the i's.
Right, knock out all the i's. So it just becomes negative 5x equals 24 minus 2y. And there we go. Now as we solve the system, this letter isn't quite by itself to use the substitution method. It's close, but I want to review with you the addition method. In the addition method, remember we said we want to get the x's, then the y's, then the equals, then the number. So how might I rearrange this top equation? Let's go back to Jamie.
4x plus y equals 25.
Good. The x, the y, the equals, the number. All right, let's do the same thing to the lower equation. X, then y, then equals, then number. Quentin?
Negative 5x plus 2y equals 24.
All right. And remember with the addition method, we said what we want to do is add the equations together so that one of the variables gets knocked out. Now, if I add them right now, I get a negative 1x and a positive 3y. No variable gets knocked out, right? But the key was to multiply one of the equations by a specific number. For instance, if I wanted to knock out the y's, I would need to multiply the top equation by a 2. That would give me what new top equation, Ethan?
X plus 2y equals 50.
And then I could also, because that would give me a 2y and a 2y. Do 2y's cancel? But maybe if I change the signs across the bottom to get what, Jamie?
Across the bottom, then you get positive 5x negative 2y negative 25.
There we go. And now when I add the equations together, now the y's cancel. Remember the addition method. All right, of course, we have to add the x's as well.
13x.
And we'll add the 50 and negative 24
26.
to get x is equal to 2. Then we can go back to either one of these equations or one of the original equations perhaps and plug in a 2 for the x. Well, negative 5 times 2, class, negative 10 is equal to 24 minus 2y. Let's again pull a double switch here. Let's bring the 2y over as a positive, send the 10 over as a to get,
34.
we end up with y is equal to
17.
17. And so we end up with 217 for my xy answer. If we wanted to, we could check that by plugging it back in here. 4 times 2 or 8 minus 25 equals negative 17. Yes, it checks out. Hey, do you remember systems of equations? Because that's essentially what a complex equation becomes, a system, real imaginary, where we knock out the i's. Let me have you work one of these on your own. Write this one down. If you would, 3x positive 3iy minus y equals 4 negative ix negative 2i. All right, check your work. Hopefully you said 3x minus y equals 4. And hopefully you also said 3iy equals negative ix negative 2i. Hopefully then you took the I out and said 3y equals negative x negative 2. So far so good? At this point, I've got a choice. I can either do addition or substitution. Quentin, what'd you do?
Addition.
You do the addition method. So you brought the x over and said x plus 3y equals negative 2. And you also said that 3x minus y equals 4. All right, and then I assume you probably multiply the top by a 3
Yes.
to get the y's to knock out. Since they already had different signs anyway, I think that'd probably be easiest. So we can say 9x minus 3y equals 12. And of course, keep the x plus 3y equals negative 2. That allows the y's to cancel. It gave you
10x,
equals, so therefore x was equal to
1.
1. Of course, we could go back and plug in the 1 here, for instance, 3 times 1.
3.
And if we move that 3 over as a negative 3, it gives you negative y equals.
1.
So therefore, y equals
Negative 1.
negative 1. And 1, negative 1 is our xy answer. Did y'all get that answer as well? All right, did you also do the addition method like Quentin, or one of you use
I
substitution?
did substitution.
All right, you substituted in the top equation maybe? Double switch y and 4?
Yes.
Okay, so you said that 3x minus 4 was equal to y.
Yes.
All right, and then you went back to the 3y equals negative x negative 2. You plug that in for the y to get 9x negative 12 equals negative x negative 2. And you end up at the same point, kind of. You still end up adding an x to a 9x to get 10x. You end up adding the 12 to the negative 2 to get 10. And you still get x equals 1. And then here, there's your negative 1 for the y. All right, questions on this? All right, you're on page 180 already. Do 31 and 33. Page 180, do 31 and 33. like I always say, you lose some, you lose some. All right, look at 31. This one's actually stupid easy. Because when you make your real equation, what does it say, Quentin?
3x equals -3.
Well, 3x plus 3 equals 0, right? And when you make your imaginary equation, it says 0 equals 69 minus 4iy. And it's really not much of a system because there's not an x in both equations. There's not a y in both equations. It's just an equation with an x and an equation with a y. So yeah, we're going to rearrange this and just say 3x equals -3 class, so that x equals -1. And we'll say that 4iy equals 16i. And we'll knock out not just the i's, but also the 4's to get y equals 4. And there's our answer, -1, 4. Did we get that? Or did it confuse us because it was so easy? It confused because it was too easy to be easy, right?
Mm-hmm.
Yeah, anyway. So, stupid easy. Annoyingly stupid easy. The next one's a little bit more like the other ones we looked at. What's that first equation going to be here, Ethan?
3x minus 4, or equals -y plus 9.
Good. And then the second equation, go ahead.
Ix equals iy plus 7y.
We're obviously in the lower equation, we're going to
Take out the i's.
take out the i's. Like Samson. All right. The neat thing is, even though this isn't set up in the usual x, y equals number layout, all like terms are lined up, and we can already cancel the y's. So I'm just going to add them as is to get
4x equals 16.
so that x equals
4.
4. And for that matter, if I plug in a 4 here, 4 equals y plus 7. Subtract away the 7 to get y equals.
-3.
And there's my answer, 4, -3 for my x and y. How many had that for 33? Questions on 33? He's looking. So while he's looking, just a reminder, technically, as long as like terms are lined up, equal signs are lined up, you can use the addition method. You don't have to bring the y's over necessarily. Did you use addition or did you use substitution?
Substitution.
All right, so you replaced the x with the y plus 7. And you said 3 times y plus 7 equals -y plus 9.
Yes.
All right, to get 3y plus 21 equals -y plus 9. And you added the y to get 4y and subtracted the 21 to get -12.
Alright, 2y.
2y. Okay, so you brought the -y over but kept it negative. Okay. All right, so we found the mistake. Any questions on this? All right, for homework this evening, I'm going to have you work on page 180, 20 to 32, the even. Page 180, numbers 20 to 32, the even. As we wrap up this first section on imaginary and complex numbers, and then tomorrow we'll get into tying trigonometry in, and we'll start to see the power. Well, it'll take a couple lessons before we start to see the power of trigonometry that it aids in complex numbers. All right, have a wonderful rest of your day, and when the bell rings, you'll be dismissed.